Welcome to the second lecture on feedback amplifiers. Today in this lecture we are going to discuss about the basic components of feedback loop and how on the basic component, that is the sampler and mixer, we are going to program the different configurations of feedback amplifier. Let's begin. So outline of today's lecture is we are going to discuss about the basic component, that is the signal source, feedback network, sampler, mixer, and how we can configure the different amplifiers like voltage series, voltage shunt, current series, current shunt, and how these configurations are directly related with whatever configurations we have already studied in lecture 1, that is the voltage amplifier, current amplifier, transconductance amplifier, and transresistance amplifier. We'll discuss the outcome of the lecture and some questions related with this particular lecture. So to begin with, this is the basic structure of a single loop feedback amplifier. We have already seen that this is the basic amplifier, which is the open loop amplifier, you can say, because if you only consider this particular block, which is nothing but A is nothing but the whatever output we are getting here and whatever input which is provided here. So output upon input provide the gain of this particular amplifier. But since we have applied some other components like signal source, this is the comparator, then the sampling network, then the feedback network, so this whole circuit is now a closed loop circuit. So this is nothing but the example of single loop feedback amplifier. Why it is called a single loop feedback amplifier? Because only one loop is involved. Now one by one we will discuss about the components. First is the signal source. Signal source can be of voltage source or current source depending upon the need. And then this is the mixture or comparator. So what is the work of mixture or comparator? Whatever feedback which we are getting, this is the feedback voltage. Whatever feedback we are getting, that has to be compared with the source voltage. So source voltage and feedback voltage is compared, or it is mixed at this particular site. So mixture or mixing or comparison is always done at the input, and relative input voltage, which is the combination of the source voltage and the feedback voltage, it gets inserted inside the basic amplifier A, and accordingly it will amplify the voltage and generate this intermediate output V, and this is the sampling network. Whenever we are taking the feedback voltage, we have to sample it, and the sampling network helps us to sample the voltage or sample the current. So in whatever form the output is, whether it is a current or whether it is a voltage, we will sample the current or voltage using this sampling network. And then through this sampling network, the current is or the voltage is applied to the feedback network. We have already discussed in detail about the feedback network in the previous lecture, but to again revise with the same thing, feedback network must be a passive network, and it has to be a resistive network in order to avoid any phase distortion between this voltage and this voltage. Whatever voltage or current which is coming from here, that has to be matched in phase with the voltage here or current here, so that there will not be any phase distortion. RL is the load resistance, and we are taking the output across the load resistance. So as I already told you, source can be voltage or current source. Feedback network is a passive, it has to be resistive. It can also be conductive or inductive, but it has to be resistive in order to avoid any phase distortion. So these two slides, current slide and the upcoming slide, are very important with respect to the analysis and derivations in this particular unit. So please be attentive while reading these two slides. First we are going to study about the sampling network, which is the sampler. Sampling network or sampler is always at the output side, and why we are interested in this sampling network, because either we can sample the voltage or we can sample the current, and the sampling is done across the RL. So whatever output which is present here, either it can be voltage or it can be in the form of current. So we are interested to sample the voltage or to sample the current. Now, depending upon the topology of the network, voltage or current may be sampled. Now, you can see that here I have written shunt and here I have written series. Remember the basic concept of voltage and current, or basic theory about voltage and current. Voltage remains same when it is on the parallel nodes, and current remains same when it flows across the series loop. So whenever we are taking the samples, what is the meaning of taking the samples? Suppose we go to the market and buy some stuff, and then we ask the shopkeeper that some kind of sample is needed. So why we are interested in that sample? Because we want to check the output, how will the output perform. So similarly here we are interested to sample the voltage or sample the current, and since the voltage remains constant or voltage remains same across the parallel nodes, we are going to sample the voltage in shunt form, and since current remains same in the series network, we are going to sample the current in the series form. This is very important, because it has exact reverse relation with the mixer circuit or the mixing circuit. So students, it is very important to understand that whenever we are sampling, we will be sampling at the output side, because we want to feed it back to the input. So sampling is always done at the output side, either in the form of voltage or in the form of current. If we are again I'm repeating, if we are sampling the voltage, it has to be in shunt form, and if we are sampling the current, it has to be in the series form. Now as I told you that the second component is going to be the mixer or the comparator, and mixing is done at the input side. And why mixing is required? Whatever feedback we are getting across this feedback network, it can be either in the form of the voltage or it can be either in the form of the current through this feedback network. Now again, as we have seen in the previous case, the mixing can be done in the form of series or it can be done in the form of the shunt. Now, unlike the previous case where we have seen that voltage is sampled across the shunt node and current is sampled across the series node. Now, when we are mixing it with the voltage source or with the current source, exact opposite case is here. When we are mixing the voltage, it is in series with, this is the series mixing, it is in series with the voltage source, and whenever we are mixing the current, that is the feedback current which is coming across this feedback network, it has to be in parallel or it has to be in shunt with the current source. Now this generates a little bit confusion that when we are sampling the voltage, then we are taking the parallel form or the shunt form, and when we are mixing the voltage, we are taking the series form. Similarly, when we are taking the sample of the current, we are taking the series form, and now when we are mixing it, we are taking the parallel form. So answer to this basic question is we know the KVL circuit and the KCL circuit. So what does KVL defines us? KVL defines us that whatever voltage source is there, it gets divided into the different resistors connected across its loop. So whenever we write the KVL equation, we write that voltage source equals to resistance into some current plus resistance into some current. I mean the voltage drops across all the resistances equal to the voltage source. Similarly, when we apply the KCL, we write the nodal equation. and in the nodal equation or in the mesh analysis, we write the source current equals to the component of all the currents, or summation of the component of all the currents. So similarly, when we are adding up the voltages or we are adding up the currents, we should remember that we are interested in summing up the voltages and summing up the currents. So similarly, likewise, you can consider that whenever you want to mix this feedback voltage, or when you want to compare this feedback voltage with this voltage source in order to generate the V in for this basic amplifier, then it has to be in series form, and when we are interested in the current amplifier, it has to be in the parallel form. Please don't get confused about this transconductors amplifier and this trans resistance amplifier. This is the basic amplifier. We will study how this transconductors and trans resistance term are coming here. Moving ahead. So first configuration is voltage series configuration. Now always remember, first term represents the sampling. First term represents the sampling, and this second term represents the mixing. So whenever we are defining any configuration, to avoid any confusion, just mug up this concept. Then when we are writing the configuration, we should remember that first term represents the sampling and second term represents the mixing. Now what we are sampling? We are sampling the voltage. And since we are sampling the voltage, what does it mean? As we have seen in the case of the sampling has to be done using the shunt network. Sorry for the interruption. So we are interested in sampling the voltage at the output side. So as we have already seen that the sampling of the voltage needs to be done in the shunt form. So you can see that the sampling is done in the shunt form. And since we are mixing the voltage, we are mixing in the series form, it has to be the voltage again. So always there is a opposite relation between mixing and the sampling. So when we are sampling the voltage, it has to be done in the shunt form, and if we are mixing it, we are mixing the voltage again. So likewise, you have to remember the configurations and how we are sampling and how we are mixing it with the input source. Now as you can see that here the voltage is at the output side and voltage is also at the input side, or from here you can see that voltage is at the output side and voltage as the input side. So what this amplifier is? Output voltage upon input voltage. So this basic voltage series configuration gives me the configuration of basic voltage amplifier. Now the second configuration is current series configuration. Again, concentrate on the first term. First is the current. So what we are going to sample now? We are going to sample the current, and again we are going to mix it the current in the series form. So current is going to be sampled, and sampling is done at the output terminal, and we are mixing it with the series, and mixing is done at the input terminal. So now since current is sampling of the current has to be done in the series type, or as in case of voltage we have used the shunt form. Since we are interested in current now, current or sampling of the current has to be done in the series form. So we have drawn the series sampling network, and whatever current is coming, we are drawing it like this. So please do not get confused about this direction of the current. Current has to be flown across the RL only, but since we are considering that the flow of the current across the feedback networks, the output current is drawn like this. So feedback network is feeding the input source through this current, and since we are sampling the current, we have applied the series sampler, and we are mixing it in the series form. So what is the interpretation of the mixing in series form? We have seen in the previous case, we are mixing the voltage again. We are mixing the voltage again. So whatever current which is coming across this feedback network, it gets converted to the feedback voltage. It gets converted to the feedback voltage. And again, this feedback voltage is mixed with the source voltage Vs. So again, whatever the combination will be, Vs minus Vf is applied as the input to this amplifier, and again the process will be done. So what is the takeaway of this particular slide is we are sampling the current, and current is sampled in the series form. So we have applied series sampler and series mixer. So both are in series. We are sampling in the series and we are mixing it in the series. This is also known as series combination, because we are sampling in the series and we are mixing it in series. So you can also call it as a sampling configuration. Now voltage shunt configuration. So again, the first term is voltage. So we are sampling the voltage, and sampling of the voltage has to be done in the shunt form. And we are interested in mixing. Now we are interested in mixing in the shunt form. So unlike the previous two cases where we were interested in mixing the feedback voltage or feedback current in the series form, here we are interested in shunt form. And whenever the shunt form of the mixing is to be applied, the mixing will be done in the form of the current. So series mixing is nothing but the voltage, like the KVL circuit. Shunt mixing is nothing but the current, like the KCL circuit. So here you can see that the diagram is of the shunt form. And why the diagram here is in the shunt form at the output? Because we are sampling the voltage. So whenever we are sampling the voltage, it has to be done in the shunt form, and whenever we are interested in shunt mixing at the input, it has to be done in the current form. Again, the opposite case. Remember these opposite cases. And how you can remember these opposite cases? Just by remembering how the sampling and how the mixing is done. What is the basic concept behind sampling and what is the basic concept behind the mixing, to avoid any confusion. Now as you can see that the output is voltage and here the input is current. So output upon input, that is the VO upon I, will give me the resistance, trans resistance amplifier. In the previous case, I forgot to tell you that in that case, when we were discussing about the current series configuration, the output was current and the input was voltage. So output current upon input voltage in the previous slide, it was nothing but the trans conductance amplifier. You can see the previous slide again if you have any confusion. Here this is the basic example of trans resistance amplifier. Similarly, this is the current shunt configuration. In current shunt configuration, again the first term is current, so we are interested in sampling the current. Again, remember how the sampling is to be done. Since we are interested in current sampling is always done in the form of series, and since we are interested in mixing it in the shunt form, so it has to be done in the form of the current again. So here this output is current since we are sampling the current, and since we are mixing the current in the shunt form, the input is also in the current form. So feedback is also in the current form. Output is current because we are interested in the sampling of the current. So output is also current and input is also current. The output upon input, and again we can say that this is the example of basic current amplifier. So it can also be known as series shunt type of configuration, because we are mixing it in the series and we are taking the output in the shunt form. So we can easily determine what are the outcomes of today's circuit. Here I have drawn a simple table to make you familiar or make you comfortable about what is sampling, what is mixing, what is the gain, and what this amplifier means for us. So whenever we are sampling the output in the form of the voltage, and when we are mixing it in the input in form of the series, so this has to be voltage upon voltage. So gain will be calculated in the form of AV, and that AV is nothing but the gain of the voltage amplifier. Again, if we are sampling the current at the output, and if we are mixing it in the form of series, so current upon voltage. So current upon voltage, current upon voltage, current upon voltage gives me the transconductance amplifier. Similarly here also, this is the output voltage, this is the mixing in the form of the shunt, and if mixing is done in the form of the shunt, it has to be I, that is the current. So the gain will be V upon I. V upon I is nothing but the trans resistance amplifier. Last is sampling of the current and mixing again in the form of the shunt. So it is I upon I, and I upon I gives me the current amplifier. So this is all about the amplifier's configuration. So in examination, it can be asked that draw and explain the feedback loop of the amplifier, and explain the operation of sampling and mixing, how sampling is performed, how mixing is performed, why sampling is done with voltage in shunt or current in series, and why mixing is just opposite to that. You would have to explain that, and then you will be asked to draw all the configurations of the amplifiers, and explain the basic features of that. So it can be either in the form of directly writing the amplifier's name, like a voltage amplifier or transconductance amplifier or trans resistance amplifier, or it can also be like asked like this: voltage series configuration, explain the current series configuration, or explain the voltage shunt configuration. So be prepared for both the type of the question, and it is easy. You can just go through the slides and just practice it in your notebook. Write down the mixing and sampling concept, and apply it for the analysis of the amplifier. So in next lecture, we will see how the derivations of input and output impedances and the gain is done of the different configurations. Thanks for watching.